So far, in our discussion in the course, we have established that the basis for working with digital systems involve the representation of electrical quantities such as voltages and currents as a set of fixed voltages. To be precise or to be specific, we saw how we can represent voltages or currents as a series of high and low voltages. So therefore, since we are representing quantities using two distinct numbers, one high, one low, or for that matter, what we call as a logic 1 or a logic 0, this shows us that the binary number system is going to be a strong influencer in the design of digital systems. So therefore, let us look at some of the number systems today, in particular binary, and how to work with them. As I already mentioned in the previous lecture, that the basis digits for the binary number system are 0 and 1. And whatever number system we discuss, we shall be comparing it with the decimal number system as a reference, because that is the number system with which we are most comfortable, because that is the number system which we have been using since we know what numbers are. So here in decimal the base is 10 and the digits go from 0 to 9. Now let us say I have a number 37 to the base 10. That means the 37 is actually a decimal number. If I want to convert it into binary, then all I need to do is keep dividing this number by 2 and note down all the remainders until we get a 0, or until the quotient becomes 0. So let's do that. I divide it by 2. So the quotient is 18 and the remainder is 1. Again I'll divide by 2. The quotient is 9 and the remainder is 0. Here the quotient will be 4 and the remainder is 1. Here the quotient will be 2 and the remainder is 0. Here the quotient is 1 and the remainder is 0. And then the quotient is 0 and the remainder is 1. So here we should stop. And we have to note down all the remainders starting from the lowest one. So go in this manner. So therefore, in binary, this is 1 0 0 1 0 1. This to the base 2. This to the base 2. This is the binary equivalent of the decimal number 37. Now, we can do a very quick sanity check also. Whether our result is correct or not, you can check also. And that sanity check will tell us how to convert the binary number into a decimal. So if you want to convert a decimal number into a binary, you keep dividing. But now if you want to convert the binary into a decimal, we can also check whether our calculation is correct. So therefore, if I have this number 1 0 0 1 0 1, this is what I have. I need to convert this into decimal. So therefore, we are going to use a very basic arithmetic concept which we have all learnt in school. That is the concept of place value. To understand place value, we need to understand the significant digits. In decimal system, each number that we are using to form the whole digit or the whole number, each of these 3 and 7, these are called as digits. But each value in binary is called a bit. what is digit in decimal is called as a bit in binary. So each binary digit is called as a bit. So therefore, just like the decimal number system, as you go more and more to the left, the place value increases or the significance of the bit increases. So just like how you have 37, this is called as a units place because the power associated with this is 10 raised to 0. This is called as a tens place because the power associated with it is 10 raised to 1 and so on. We are using the base of 10 because this is the decimal number system. But since this is binary, we need to use the number system 2 as a base. So therefore, this is called as the units place. This is called as the 2th place. This is called as the 4th place and so on. So therefore, if you want to calculate what the number is, simply it will be 1 into 2 raised to 5. These two are zeros, so they will not have any effect. Plus 1 into 2 square. Again, this is 0. Here it will be 1 into 2 raised to 0. So therefore, this is 32 plus 4 plus 1, which is nothing but 37. So this is what is our original decimal number. This is what is our original decimal number. Now, let us look at a couple of small but important conventions. Suppose we have this number 100101. This rightmost bit is called as the LSB and the leftmost bit is called as the MSB. This means least significant bit. And obviously this would mean the most significant bit. Right? So, in fact, this is how we denote digits in any number system. Most significant digit, least significant digit. Just that in binary, we call it as bit. So, if anybody gives you a decimal number and asks you to find out what is the binary equivalent, you can keep dividing by 2. Now, while this may seem very simple, this process becomes more and more tedious as the number increases in value. So, this one is 37 in decimal. If the number becomes, let us say, a 3-digit number or a 4-digit number, if you sit and start dividing by 2, you will probably fall short of pages. You will probably fall short of space. And therefore, the calculation would definitely become quite tedious. So therefore, the question now is that is there any other way in which we could convert a decimal number into a binary number without continuously dividing by 2? Let us say we will take the decimal number 56 and we want to convert this into binary. Well, to have this converted into binary, the first step is identify the next lowest power of 2 for this number. So powers of 2 are what? 1, 2, 4, 8, 16, 32, 64. 64 becomes more than 56. So therefore we will choose the next lowest power of 2, or I should say lower power of 2. So therefore in this case it will be 32. The step 2 is list all powers of 2 in descending order from point number 1. So we identified 32. So therefore 32, 16, 8, 4, 2, 1. We are going to write it like this from left to right. And third step is assign ones where needed. Now what this means, we have to assign ones in such a way that the place value of each bit when added with others gives you this number. So therefore, since we want to make 56, we will put 1 over here, 32, because we definitely need this. If I don't put 1 over here, notice what is remaining. 16 plus 8 is 24, plus 4, 28, plus 2, 30, plus 1, 31. So therefore, unless we use this, we can never ever reach 56. Okay, so I'm going to put 1 over here. So I should say assign ones where needed and obtain sum of all place values. And that should be equal to the original number needed. Now, if I am having a 1 over here, that means the place value is 32. So definitely we are falling short. We need 24 more. So therefore, I'm going to put one more 1 over here. So therefore now the sum of place values becomes 32 plus 16, which is 48. I'm still falling short. I'm falling short by how much? I'm falling short by 8. Because right now I'm at 48. I need 8 more. So therefore all I need to do is place a 1 over here. And the rest will be 0. And the rest will be 0. So therefore 56 in decimal becomes 111, 000 in binary. It's as simple as that. Let me explain this with one more example. Let me explain this with one more example. Let us say I have the number 875, which is a pretty big number. So therefore again I cannot keep dividing by 2. So therefore let us try to follow those steps which we did for the previous example. Step 1 is to identify the next lower power of 2 from this number. So the next lower power of 2 would be 512. Yes, it will be 512. So I'm going to start with 512 and then write all the lower powers from there left to right. 256, then 128, then 64, then 32, 16, 8, 4, 2 and 1. So if I need to make 875, let me put a 1 over 512. So therefore, we have 512 which is needed to make 875. The next question is, do we need 256? Let us add these two. 512 plus 256 gives us 768, which is less than 875. So definitely we will need 256. Do we need 128? Let us add 128 over here. Here the sum becomes 896, which is more than what we need. So therefore we should not add 128. So therefore I'm going to put a 0 over here. So then let me check if 64 is needed. We get 832. which is less than 875. So therefore I'm going to put a 1 over here. Then is 32 needed? We will add 32 over here. We get 864, which is still less than 875. So we will put a 1 over here. Then we have to see whether we need 16. Here we will get 880. So this is not needed. 16 is not needed. So therefore we will put a 0 over here. Now we'll have to check for 8. We'll get 872, which is less than 875. So we're going to put a 1 over here. Now how much is left? Only 3 we need. So we will not put anything at 4, but we will put 1 because 2 plus 1 is 3. So therefore the net binary number would be 110 to the base 2, where this is the LSB and this is the MSB. So this is one example, one additional example through which we can convert a decimal number into a binary number without having to continuously divide by 2 and lose track of the space. So therefore, to repeat, if you are converting a decimal number into a binary number, identify the power of 2 that is closest to the number you need but lower than value. And then list all the powers of 2 from that identified power in descending order. Then assign ones to each place value as and when needed until the sum of each individual place value becomes equal to the number you need. Now, using this concept, let us look at now what is the hexadecimal number system. The hexadecimal system has a base of 16. That means there are 15 base digits because n is 16. Right? So therefore, the base digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now after 9, we have 10, 11, 12, 13, 14, 15. But they are not digits anymore. They are numbers which consist of 2 digits. So the hexadecimal system assigns an alphabetical letter to each number above 10. So 10 is called as A, 11 is called as B, 12 is called as C, 13 is called as D, 14 is E, and 15 is F. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You have 16 digits going from 0 to F, which are the basis digits. So effectively A means 10 and F means 15. And all the other numbers from 10 to 15 belong in the middle of these two. So again, let us take this number 875 to the base of 10 and convert it to the hexadecimal base of 16. So the other way to do it, the standard way to do this is to divide by 16. Just like for binary, how we divide by 2, we will divide this by 16. So 16 5s are 80. So 4. 16 4s are 64. So what we will do, So 5 and 4. This will be the quotient. And the remainder will be 875 minus 864, which is 11. Then I will again divide by 16. So 16 3s are 48. and remainder is 6. Again, I will divide by 16. Quotient is 0 and remainder will be 3. Now, the moment we notice the remainder is 11, we have to assign a letter to it. So therefore, 11 will be B. So the hexadecimal equivalent will be 36B. This is how we can represent a hexadecimal number. Now you may be curious about why we are introducing letters along with the numbers and creating additional confusion. Definitely, you can ask that. Definitely, you can ask that. Now, there is a very subtle relationship between, or not very subtle, there's a very strong relationship between the hexadecimal system and the binary system. What I mean to say is that if you have a binary number or you have a hexadecimal number, you can convert binary to hexadecimal and hexadecimal to binary very easily. Very easily. Without having to convert them into the decimal system first. And that's a very powerful tool. That is why many computers, if they have to represent a large number of or some large number using a series of high and low voltages or a series of ones and zeros, writing in binary may be okay for the computer. But if the computer is showing that answer or that number to the user that has a large number of ones and zeros, for the user, for the human being, looking and working with so many binary digits can be very, very cumbersome, can be very, very tedious or difficult. So therefore, what computers do is that without having to do any further computation, they take the binary result and show it to the user as a hexadecimal form. Okay. So to do this, let us see how. So let us look at this 875 to the base 10 and look at what the binary version of it is. So we had derived that 11 0 11 0 10 11. This was the binary equivalent of 875. So let's write this. This is in binary. Now, what you do, you start from the rightmost side and group 4 bits at a time. So we will make one group over here, one group over here. Now what is happening here? We have just 2 bits. So we need to make a group of 4 bits. So what we will do, we will augment zeros over here because they are not adding to any other value in the significant position. So therefore this becomes a third group. Now what you do, you take each group and convert it into its equivalent decimal or hexadecimal value. So 0011 means in decimal it is 3. 0110, how much will it be? It is 4 plus 2, that is 6. 1011, how much will it be in decimal? 8 plus 2 plus 1, that is 11. That is 11, so therefore in hex it becomes B, which is exactly the same as what we had obtained. So therefore, rather than writing 12 binary bits, I can write 3 hexadecimal digits, which can be more easily understood by a human being. So this is how we can convert from binary to hexadecimal. So to do the opposite, if I have a hexadecimal digit, let us say, which I want to convert to binary, let us say I have this digit A239. This is hexadecimal. I want to convert this into binary. So to convert this into binary, take each hexadecimal digit and write its 4-bit binary form. So A is 10. So therefore 10 is 1010. Of course, I am doing it very fast because I know you will initially have to take some time to calculate the 4-bit binary for each of these digits. But after you get the practice, you can also do it very, very quickly. 2 will be 0010. 3 will be 0011 and 9 is 1001. So therefore the net number will be 1010, then 0010, then 0011, then 1001. This is the net number in binary. The computer finds this easier to read, whereas we human beings would probably find this more easier to read. So therefore we saw how to represent binary numbers and how to use hexadecimal numbers and convert into binary without really having to go through the decimal number system. You can also convert from hexadecimal to binary or binary to hexadecimal without going through the decimal base. Now, let us ask the next question. That is, so far, when we were working with numbers to convert from decimal to binary, binary to decimal, what about fractional numbers? So therefore, let me go to a new page. Suppose I have a decimal number, let us say 57.25 to the base 10, where this indicates a fractional point or a decimal point. So to convert this into binary, the process is fairly simple. Again, we will take the integer part, that is 57. So what is the closest power of 2 to 57? It is 32. So therefore we will write 32, 16, 8, 4, 2, 1. So this is the integer part. Now this is 2 raised to 0, this is 2 raised to 5. To represent decimal points, you will need to write the powers of 2 raised to minus 1, 2 raised to power minus 2 and so on. So this becomes half, this becomes 1 by 4 and so on. So for 57, we will be representing it using the left part of this decimal point. So this line is where the hypothetical point is. So for 57, we get 32 plus 1648 plus 856 plus 157. So this is straightforward. Now we have the 0.25. What to do with this? 0.25 in this case is pretty easy because I can see this 1 by 4 is nothing but 0.25. So therefore I can put a 1 over here and a 0 over here. So therefore what we are getting, the whole binary number is this with a base of 2. Now, this was pure luck through which we saw that one of the powers of 2 is indeed this. Now, what if it is something little more complex? Let us say it's 0.27. Suppose we have this number 57.27. The 57 representation will not change. Now we need to look at 0.27. So let us say we take 0.27, the way it is. What you do is just multiply it with 2. What do you get? You get 0.54. This 0, you note it down. This corresponds to the 2 raised to minus 1 point. Then take this thing, 0.54 into 2. You will get 1.08. Now note this one down. This is for the 2 raised to minus 2 position. And take this and go again. 0.08 into 2. The 1 is removed. We will just use 0.08. This is 0.16. This becomes the 2 raised to minus 3 position. And so on. So on until you reach a 0 in the main number, or you get the desired degree of precision that you want. So therefore, in this case, it will essentially be a recurring decimal. To some point, you will have many binary bits. So let us stop at 3 positions. So what this number will essentially be in binary is that the integer portion will not change, that is 111,001 point. Now note this down. 0, 1, 0, and so on. You can just put you can just stop over here. You will lose some precision definitely. If you want to go for more precision, you need to keep multiplying by 2 until you reach a 1. But that I leave to you as a further exercise. So these kind of representations for fractional numbers are called binary, fixed point representation. And it is used by many processors to denote fractional quantities. Well, having established some of these basics, let us now move on to bigger and better things. That is, let us move on to what is binary addition. So to add binary numbers, the rules are very simple. There are just 2 digits or 2 bits, 0 and 1. So the rules are very simple. 0 plus 0 is 0. 0 plus 1 is 1. Now here I mean addition. This is not OR. Here I am actually doing addition, not OR. So be careful over here. 1 plus 0 is 1. So far it is just like our decimal system. Now what about 1 plus 1? 1 plus 1 in decimal is 2. So therefore, we need to convert 2 into binary. So 2 in binary is what? It is 1 and 0. 1 plus 1 is 1, 0. So therefore what we are seeing is that for the first 3 cases, when we are adding single bits, the answer is also a single bit. But when we are adding over here 2 bits, each of 1, the answer is 2 bits. So therefore, this left bit is called as the carry or carryover. It is also called as the carry bit. Now this is very, very simple to understand when you look at it from the decimal perspective. The addition rules that we have learned since the time when we were all children, we also had the concept of carry. So in binary, when you have 1 plus 1, you get a 0 and a carry of 1, which comes on the left hand position. Compare this with 2 decimal numbers, let us say 9 and 5 in decimal. 9 plus 5 becomes 4 with a carry of 1. Of course, we call it 14, but this one is a carry. Like this is a carry. Of course, since this position denotes a sum, we will call this a sum, which is the case for the first three also. The bit that you get all the time after addition is called as the sum. Any additional bits on the left is called as the carry bit. Right. So let us take one more example in decimal when we are adding two numbers, let us say 36 and 67. So when we are adding in decimal, what we do is this. 6 plus 7, 3 with a carry of 1. So this one sort of comes over here. Then you have 1 plus 3, 4 plus 6, 10. So therefore this is now the carry. Let us look at how to do this. In binary. But before going to binary, let us take one more example just to show whether our decimal understanding is clear or not. Let's say I have 39 to the base of 10 plus 67 to the base of 10. So therefore we have 39 plus 67. So 9 plus 7, we have 6 with a carry of 1. Again we have 1 0. This is the carry bit. So let us now do this in binary. So we have 39 and we have 67. The first step is we need to convert this into binary. So very quickly we can convert. So 39, the closest power of 2 is 32. So we'll say 32, 16, 8, 4, 2 and 1. So 32 and we need 7, it is this. 67, the closest power of 2 is 64. So we have this over here. 64, we need just 3 more, so 1 and 1. So what we'll do, we'll just add a 0 for the first number to make the number of bits equal in both cases. And that's it. Now we will add. Start the addition from right, the way we normally do. 1 plus 1 is 0 with a carry of 1, as we have established. The sum is 0 and the carry is 1. Now 1 plus 1 is again 0. But the carry of 1 is generated and it goes over here. So 1 plus 1 is 0. When you add it with this one, you get 1. Now we have 1 plus 1, which is 0. And a carry of 1 goes. This becomes 1. Here there is no question of any carry. This is 0. This is 1. This is 1. Now we have this sum. It does not have any final carryover, but there are some intermediate carries. For example, here, here and here. So now we need to see what this final number is. So this is, just put the place values, 64 plus 32 plus 8 plus 2. 96 plus 8, 104 plus 2, that is 106. That's it. We have got the answer, which is exactly matching with what is our answer in the case of decimal. Now, this is how to do binary addition. Let us take one more example. Let us say we have, now let's just put some binary numbers. Let's not get into decimal. We'll say 1 0 1 0 1 1 1 0. The next number is 1 1 1 0 1 1 0 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 with a carry of 1. Now, we have 1 plus 1 which is 0 and a carry of 1 is generated. This 1 plus 1 0 will now be added with this one, which will give me a 1. Here it is 1 plus all zeros, so it will be 1. 1 plus 1 is 0 with a carry of 1. Here again we will get a 0 with a carry of 1. 1 plus 1 will give me a carry of 1 which will come over here, and this remaining 0 will be added with this 1, which is 1. Okay. So this additional carry comes over here. This is called as the carry over. So this is one classic example where you are having one additional bit in excess to what is there in each of the numbers. So if you notice, each of these numbers has 8 bits. 1 2 3 4 5 6 7 8. Here also 1 2 3 4 5 6 7 8, but the result is a 9-bit number. 1 2 3 4 5 6 7 8 9. So we say 1 bit of carry and 8 bits of sum. Is that fine? So you can again cross-check this with the decimal system by converting this into its decimal form. So the first number and second number you can convert. 1, this will be 8, 16, 32, 64 and 128. So the number will be 128 plus 32, that's 160, plus 8, 168, plus 4, 172, plus 2, 174. I think this is the one it should be. This one, 128 plus 64. How much is that? 192. Plus 32. 224 plus 8, that is 232, plus 4 plus 1, that is 237. So when we are adding in decimal, we will get 4 plus 7, 11, 1 goes over here. Again we will get a 1, 4, 4, 1, 1. So here, this will now be position 256. 256 plus 128. 384. 384 plus 16 is 400 plus 8 is 408 plus 2 410 plus 1 411, which is exactly what we had got earlier. So this is the way in which you can do binary addition quite easily and cross-verify it with the decimal number system. So we shall stop here for this particular lecture and we shall continue in the next lecture. Thank you.